When people think of aliens, they imagine organisms. Science begins somewhere smaller. Organic molecules. The rover Perseverance is not searching for little green creatures. It is searching for chemical traces. In Jezero Crater, once an ancient lake, Perseverance has detected organic compounds embedded in sedimentary rocks. Organic molecules are carbon-based. They are the chemical backbone of life on Earth. But organics are not proof of life. They can form through non-biological processes. Meteorites contain organics. Interstellar clouds contain organics. The real question is structure. Are these molecules randomly assembled, or do they show patterns consistent with biological processes? Perseverance is collecting rock samples that will eventually be returned to Earth. Those samples may reveal isotopic ratios, molecular complexity, and structural clues. Another puzzle, methane. Methane has been detected in Mars' atmosphere in fluctuating amounts. On Earth, methane is strongly associated with biology, but also geology. The mystery is variability. Why does methane appear seasonally and then disappear? If it were geological, we would expect more consistency. If biological, we would expect localization. We do not yet know. Mars has not revealed life, but it has revealed chemistry that keeps the question open. If Mars represents a dry memory of habitability, other moons represent hidden possibility. Two worlds stand out: Europa and Enceladus. Both possess subsurface oceans beneath thick ice shells. The spacecraft Cassini-Huygens flew through geysers erupting from Enceladus and detected water vapor, salt, organic molecules, molecular hydrogen. Hydrogen is critical. On Earth, hydrothermal vents on the ocean floor use hydrogen as an energy source for microbial life. If similar hydrothermal systems exist beneath Enceladus ice, conditions for microbial ecosystems could exist. Europa likely hosts a global ocean beneath its frozen crust. Tidal heating from Jupiter's gravity provides energy. Water plus energy plus chemistry. Three fundamental ingredients for life. We have not drilled through the ice. We have not sampled the ocean directly. But plumes and gravitational measurements strongly support subsurface oceans. Life, if it exists there, would not be intelligent. It would likely be microbial. But microbial life elsewhere would fundamentally change biology. Life would no longer be uniquely terrestrial. Humanity is not guessing blindly. We are building missions. Europa Clipper will perform detailed reconnaissance of Europa. It will map ice thickness, analyze surface chemistry, and search for active plumes. In the Saturn system, follow-up missions are being studied. These missions do not promise alien life headlines. They promise data. Precise measurements of ice dynamics, chemical composition mapping, thermal activity detection. Science advances through instrumentation. The strategy is clear. Confirm ocean stability. Identify energy sources. Analyze chemistry. Assess habitability. Only then can stronger claims be made. There is a difference between habitability and life. Habitability means conditions allow life. Life means biology is present. So far we have confirmed. Past water on Mars. Subsurface oceans on icy moons. Organic chemistry across the solar system. We have not confirmed living organisms. But the shift is profound. For centuries, alien life was speculative philosophy. Today it is a testable scientific question. We now know that water is common. Organic chemistry is widespread. Energy sources exist beyond Earth. The solar system is not sterile rock. It is chemically active. The next decade may determine whether any of these environments cross the boundary from chemistry to biology. In 1995, the first exoplanet orbiting a sun-like star was confirmed. Since then, thousands have been discovered. Some are gas giants. Some are super-Earths. Some orbit within their star's habitable zone. The habitable zone is not a guarantee of life. It is simply the region where temperatures may allow liquid water on the surface. Planets like TRAPPIST-1e, Kepler-452b, and others have drawn attention. But discovering a planet is only the beginning. The next step is analyzing its atmosphere. If life exists elsewhere, it may alter atmospheric chemistry. That alteration could be detectable across light years. When a planet passes in front of its star, some starlight filters through the planet's atmosphere. Different gases absorb specific wavelengths. This creates a spectral fingerprint. The James Webb Space Telescope has begun analyzing exoplanet atmospheres in unprecedented detail. JWST has detected water vapor, carbon dioxide, methane, clouds and haze. These detections are not evidence of life, but they demonstrate capability. The goal is to identify biosignature combinations. For example, on Earth, oxygen and methane coexist because life continuously replenishes them. Without life, these gases would react and disappear. Finding such chemical disequilibrium on another planet would be significant. But caution is critical. Non-biological processes can mimic biological signals. Not every oxygen signal means forests. Not every methane signal means microbes. Ultraviolet radiation can split water molecules, producing oxygen abiotically. Volcanism can release methane. Planetary geology can generate complex chemistry. Astrobiology requires context. Temperature, pressure, stellar activity, planetary mass, all matter. The challenge is not detection. It is interpretation. Future telescopes will increase resolution and sensitivity. The Roman Space Telescope and proposed large UV optical missions may directly image Earth-like planets. Direct imaging would allow atmospheric characterization without relying only on transits. Each improvement reduces ambiguity. But ambiguity remains central to scientific caution. We are not detecting cities. We are detecting chemistry. But the speed of advancement is accelerating. 30 years ago, we did not know whether other planets existed. Today, we measure atmospheric composition across interstellar distances. In the coming decades, larger space telescopes, starshade missions, high-contrast coronagraphs, more precise spectrometers, may push detection thresholds further. Alien life detection will likely not be dramatic. It will be statistical, a signal that persists, a chemical imbalance that resists abiotic explanation. Science will move cautiously, because extraordinary claims require extraordinary evidence. If microbial life might be common, intelligent life is a different question. Instead of searching for chemistry, scientists search for signals. This field is often called SETI, the search for extraterrestrial intelligence. Modern SETI does not rely on random listening. It uses advanced radio arrays capable of scanning billions of frequencies simultaneously. Facilities like large radio telescope arrays continuously monitor the sky. They search for narrowband signals, transmissions that stand out from natural cosmic noise. Natural astrophysical sources tend to emit broadband radiation. Artificial signals are typically narrow and structured. So far, no confirmed artificial signal has been detected. There have been intriguing anomalies, but each has eventually been explained as terrestrial interference or natural astrophysical phenomena. Silence does not mean emptiness. It means we have not detected anything unambiguously artificial. The search continues. Radio waves are not the only possibility. Advanced civilizations might use lasers for communication. Laser pulses can travel vast distances with minimal dispersion. Optical SETI searches for extremely short, intense bursts of light. These bursts would differ from natural stellar variability. Some observatories now include optical detection systems. They monitor nearby stars for nanosecond-scale flashes. Again, no confirmed artificial laser has been observed. But detection sensitivity improves with technology. As instrumentation advances, smaller and more distant signals become detectable. Each improvement expands the search volume. In recent years, astronomers have detected extremely powerful millisecond signals known as fast radio bursts. Some initially speculated about artificial origins. Further analysis revealed natural explanations. Many FRBs originate from magnetars, highly magnetized neutron stars. The lesson is important. Unusual does not mean artificial. Astrophysics often produces signals more extreme than science fiction. Caution is essential. Extraordinary signals require extraordinary verification. The universe produces phenomena we once considered impossible. Understanding them requires patience. If intelligent civilizations are common, why have we not detected them? This question is often summarized as the Fermi paradox. But the paradox may not be a paradox. Our search window is small. Modern radio technology is barely a century old. We have surveyed only a tiny fraction of the galaxy's stars at limited sensitivity. Civilizations may be rare. They may be short-lived. They may not use technologies we recognize. Or they may communicate in ways indistinguishable from natural phenomena. Silence is data, but incomplete data. The search for intelligent life is not about belief. It is about measurement. And measurement takes time.